chemistry uses instruments and methods to study separation, identification, quantification, and statistical treatment of the components of matter. So this is the textbook definition. So again, please don't write that definition down. Where is analytical chemistry used? So let's just kind of brainstorm. Where might you need to separate, identify, quantify, or use statistics in chemistry? Or not in chemistry?
Determining purity.
Purity? Let's bigger picture though. Where would we do that? Industry? What industries?
Pharmaceutical.
Pharmaceutical and chemical industries. Yeah, perfect. So pharma. Hopefully the people making our drugs care about how pure they are. Industry in terms of chemical industry, we can do that. Any other ideas?
Meth labs.
Oh. Well, meth labs are probably more organic. They probably don't actually care.
That's funny.
About the identification or how pure their stuff is, unless it's good meth. So possibly. We're going to leave that to Dr. Monso's organic chemistry class though. So food labs. Also quality assurance. Have you guys heard that word before?
Yeah, for sure.
Quality assurance, almost any forward-facing company, if they make food, if they make drugs, if they make anything that we use on our body, lotions and stuff like that, have a quality assurance department, and they basically are testing what's in the thing, the consumer product, to make sure it doesn't have bad stuff in it. So quality assurance. If I flip it this way, is it really going to do that? Okay. Environmental is a huge field that also uses analytical chemistry. Crime labs, forensics, huge field that uses analytical chemistry. And then I'm going to say just research in general, we're probably whoever said industry at the beginning, that kind of field. So coming up with ideas, trying to figure out what it is, how to do it. So analytical chemistry is used a lot. It really is one of the foundational chemistries. I, as an analytical chemist, would argue it's probably one of what you have, forget general, but organic, analytical, inorganic, P-chem, and biochem. That's everything, right?
Inorganic, analytical, P-chem, and
whatever they are, the 6 or 5. Analytical is the one that every chemist actually uses at some point, because it's qualitative and quantitative. So we are going to use this language a lot in the class. Qualitative deals with the identification of matter. And quantitative deals with the amount. So qualitative is the what is it question. What is it? So if we're in a forensics lab, is there codeine in the victim's urine? Is it that's just a what is it? Is there codeine in the urine? Quantitative is the how much. So going back to forensics, that might be, is the amount of alcohol in their blood past the legal limit? So not only is there alcohol in the blood, but how much of it is there in the blood? So the what is it and the how much are two different questions in analytical. So codeine in urine, possibly? How much? Alcohol in the blood. Because that would determine if something's illegal or not, depending on the how much. So we are going to use qualitative and quantitative throughout the semester. Most of our labs will be quantitative labs, so we're actually trying to figure out like the how much. If you continue and you need to take instrumental chemistry, that's when you start doing some qualitative labs as well. Just like if I give you a soil sample and I say, is there lead? And you have to figure out if there's lead, that's just qualitative. Yes, there's lead, no, there's lead. Then you can have the follow-up question, how much lead? It's a quantitative question. So we will use that language a lot, qualitative and quantitative. So that was our little intro to analytical chemistry. And then probably at the beginning of like every chemistry class, we like just go over our prefixes because we love prefixes. Can you guys see that in the back? Yeah, okay, because I can't see it over there, but I guess the screen's bigger. So we will be doing lots of calculations because it's a quantitative class, so we're gonna have a lot of how much questions. So we are going to use a lot of conversions. So this is like our table of the prefixes. If at this point you don't have these memorized, I'm just going to start, oh my gosh, welcome to me again. Okay, I'm just going to star the ones that you need to know for this class. So like the kilo is 10 to the 3, and then the milli, micro, and nano. So those are the ones that we will be using many, many times in this class. Okay, so with that, we are going to start our first quantitative question. These are kind of like simple, but before we start, I'm actually going to kind of go over a problem-solving technique that we'll be using throughout the class. It might seem silly for this one, but when we get to our more complex ones, you'll see. But it's called goal, and it was like in our syllabus. But the first thing that you need to do when you read the question is just figure out what information you're given and what you're trying to figure out, which I'm sure you all do, but just you might not recognize that you do that. So if we just look at like our first problem, A, convert 5 times 10 to the 5th meters to kilometers, what information are we given? And you can just call it out.
Times 10 to the 5th meters.
Beautiful. So I usually underline what I'm given. Where am I trying to go? What am I trying to figure out? Kilometers. And I usually just circle where I'm trying to go. This helps me because after like you've done a question and you've kind of like forgotten what the point was, you can be like, is my unit what I circled? And then you can like test if you're on the right track. So we're trying to go meters to kilometers. What piece of information do we know to get from meters to kilometers? The prefix. So in this one, this question is our prefix. So we would look at our kilometers and we have 10 to the 3. So then we start to set up our dimensional analysis. And I don't know who you guys had for Gen Chem, but it's dimensional analysis, or it's called like railroad tracks or train tracks, or I'm not really sure what it's called. But it's how you set it up so your units cancel. And I am going to be a stickler on this. I'm not going to like take points off, but I'm going to harp on you. So we write what we're given, 5 times 10 to the 5th meters. Always write your unit, times, and then I just fill in my conversion factor. So here someone said we're going to use our prefixes. We need our units to cancel, so meters is going to go on the bottom. Kilometers, kilometers is going to go on the top, and then we can like fill in our prefix. So there's 10 to the 3 or 1,000 meters in 1 kilometer. And then our units cancel and we are in kilometers, which is what we circled. So do we want to get our calculators out or do it in your head if you're a exponential expert? 5 times 10 to the 2. I do this thing in my class where it's called second or different. We do a lot of calculations. So basically every calculation, someone shouts out an answer and then I ask the class second or different. If you got the same thing, you say second, like you second that response. Or if you got something different, you can shout out the different thing you got, and then I kind of go to the class and say, like, which one of these have you gotten? So because of that, we are shouting out numbers at each other a lot, and because we are all like really cool people who know like calculators are challenging, there is no judgment if someone shouts out the wrong answer, because we've all been there, and we just move on, correct? No judgment? Great. So we have a 5 times 10 to the 2. Do we have a second or a different? Second? Awesome. And that's when I box it. 5 times 10 to the 2, also known as 500 kilometers. So take a minute and do the next one. 3 times 10 to the negative 8 grams, and convert it to micrograms. And if you don't have a calculator, you can set it up. Then on Wednesday you'll all okay, shout out when you get it. When you get something.
3 times 10 to the negative 2 micrograms.
Second.
Microgram, second. 1, loved how we said the unit with that number, so kudos. 3 times 10 to the negative 2 micrograms. Awesome. And just, I'm like a weirdo. I do the smaller thing into the bigger thing. It just helps me. So if I ever confuse you, sorry about that. So I write it 10 to the 6 of the smaller thing in the bigger thing, instead of 10 to the minus 6 being on the bottom. Awesome. So you're experts there. Okay, so now we're going to talk about uncertainty in measurements. Depending on who you had for Gen Chem, you might have heard this, but this class is like we're going to hear it and you're going to keep hearing it, because this is a big thing to do in analytical, is how certain are we in that number. If you think about it, like the blood alcohol, if you're going to send someone to prison, to jail for doing something wrong, you need to be pretty certain in the value that you're figuring out. So we care about uncertainty in measurements, and one of the things that tells us how certain a measurement is significant figures. So I call these Sig Figs, so you'll hear me say that, or if I write on the side of your paper, I might just write Sig Fig. I'm talking about significant figures. So this is the minimum number of digits needed for a given value without loss of precision. So that is the important part here, without loss of precision. So here we have 3 numbers written, and this is to remind us. Have we all seen this somewhere? Like, you should have in Gen Chem, but like we all get taught by different people, so I don't actually know. So trailing zeros after a decimal are significant. So they're there on purpose. So they're telling you how precise that measurement is. So trailing zeros are significant after a decimal. So when you say like 1,000, those aren't trailing zeros. That number only has one significant figure. It's the 1 in the 1,000. If you say 1,000 with a decimal after it, now those zeros are significant.
So does it mean that also before a decimal as well, they're significant if you put...
Yeah, so decimals are important. Yeah, so but only before if there is like a decimal placed there. So yeah, if there's a decimal, then before. And then if you start adding the zeros after, those are significant if they're added after the decimal. So this number here only has 3 significant figures, where this number here has 5 significant figures. So up to now, you might have been like, those are the same number. But now in analytical chemistry, I'm telling you those actually mean different things. So 3 Sig Figs. If you were to write this out, the 0s, 2, 3. The zeros before are just placeholders, so those are not significant, but these ones are. So hopefully that was like kind of a reminder into Sig Figs. But we care about that now. And especially in lab, when you guys start taking measurements, we care about significant figures. So where do those significant figures come from when we're in lab? So we read a lot of glassware in lab, you take a lot of volume measurements, mass measurements, all of those have a certain amount of significance. So if we're looking at this beaker here filled with water, we know for certain that this water level is somewhere between 40 and 50 based on the graduations of the beaker. And then we get to interpolate. Do we remember this word? I find this word fun. Interpolate.
It's not the.
Yes, no, have you heard that one before? The guess, the estimate. So we get to interpolate how close it is. So shout out how much water is in this beaker. 48 milliliters, hopefully, but you're right. This beaker is not labeled. Seconds difference. Okay, so if you said 47, like that's also correct, because once that interpolation, you get, like everybody could have a little bit different of an interpolation, and that's why, like, we start to lose significance. So 48, 47 milliliters, both of those are correct. If you told me 48.5, I would just laugh at you because you already, I wouldn't really, I'm sorry, but you already lost precision in this number because everyone is already guessing where they think it is. So there's no point in telling me one more significant figure because you don't know. So that's why it's important in analytical chemistry in terms of like the significance, the precision of the value. So take a minute if you can from the back, I don't know. What about this burette? How much is in this burette? Zoom. I don't know if that helps. Huh. There's Is that better?
Oh, they're each the meniscus. Yeah, I did that they're all
Yes,
2
from the bottom of the meniscus, correct. That's where we take our measurement.
29.1.
The bottom of the sloopy thing.
2.
So just shout out if you have a number. 1.5. A second or difference?
Second.
I wrote it the wrong way. That's okay.
What's our second? You second 29.15? Sure. Well, I'm going to send you all back to Gen Chem. 28, 29, 30.
Oh,
so it's
forgot.
between
It's
the
a
28 and the
titration
29.
It's a titration too.
So it, okay, so let's breathe, let's pause, everyone.
That's funny.
That is hilarious.
Let's try
I was
again.
reading it up, but I didn't look at the top.
Burettes are tricky like that. That's why I put a burette in.
That was smart.
That's funny.
So 28.
Now shout out what you think.
28.8.
28.9.
That makes more sense.
You didn't say another.
Yeah, we get one more because we know for certain. Or if you think it's 28.9, that means like you think it's right on that line. So that would be 28.90. I think it falls a little bit above the line, so I know for certain it's between 28 and 29. And 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's between the 0.8 and the 0.9. So I know that for certain, and then I get one more number to interpolate, to guess.
Like 0.8 or 0.7?
So 0.8 or 0.7 I heard. If you wrote 28.90, I'd still give you credit for that. If you wrote 28.9, I would be like, they don't know what they're doing. So, but if you put that 0 there, I would just assume you saw the meniscus on that line. And our unit here is milliliters. But this kind of goes, like, you could have also said like 28.83 milliliters. I mean, it just depends how you see that meniscus, if it's like closer or farther. And when you're actually in the lab, your meniscus can move based on your eye level, right? Like if you're looking at it straight on or not. And that's why this number can change. So we lose our precision in that position. for that piece of glassware. So which of these, beaker or burette, is more precise? Burette. Wonderful. Perfect answer. Yep, so our burette is more precise. So in analytical chemistry, you're only going to use beakers as like solution holders. Like you'll never do a measurement or anything in a beaker because they're really good at holding solutions, and that's about it. We don't do measurements. Okay, so we are going to stop there for today. To kind of get us started. So please don't check with the bookstore today because I think I've thoroughly annoyed them. But tomorrow, please check with the bookstore. They said they're getting some stuff in from the printer today, so hopefully it's there tomorrow. And of course, if it's not there by Wednesday, we'll tackle that problem when we get there.
Thank you, Dr.
Yeah, I'll see you guys all tomorrow in lab. Okay.
So I won't be here
On what day?
on the 14th. So I got Friday, so I know I'm Zoom.
Okay.
And then I won't be here Monday, Tuesday, Wednesday. So if there's like a time that I can figure out.
Yeah, so let's touch base. We'll figure that. But thank you for letting me know. Just let me know the date.